I don't want to be held accountable for that. All right, so I need to take some classes on being a better motivational speaker. You know, I really do. Try and motivate everyone instead of like demoralizing everyone. Just try to be honest, though. All right, so what does the product rule say? If you have two functions that are being multiplied and you want to find their derivative using a shortcut, the derivative will be what?
The derivative of f of x.
The derivative of f of x, which I'm just going to say f prime times g plus g prime times f. And that's the way I recommended you learn the formula, right? And I proved this in class. I proved it. I used the limit definition. I proved that. If any of you turned in the bonus, I haven't looked at them yet. So I just got all the exams graded, and then I'll go figure out everything else later. All right? Because I asked you to prove what? Cosine? Right? Derivative cosine was negative sine, and something like that. Yeah. All right. So that is the rule. That is the product rule. Let's get warmed up because it's been a whole week since we've actually talked about this. Let's do an example. An example of this, let's say we have a function. I'm going to call it h of x is equal to x to the fifth sine x. I would like for us to find h prime of x. That's a good marker. Yeah, it's going to run out now. All right, so let's take it slow, okay? Let's take it slow. The derivative of h should be a product, right? Does everyone see where the product is occurring? Between what two factors? The x to the fifth and the sine, right? There's a multiplication right here, right? That's the only multiplication in the problem? That's not multiplication, right? Sin times x, no, that's sine of x, right? So that's the only multiplication in the entire problem right there. So according to the product rule, if we call this first thing, x to the fifth, if we call that f, and we call the sine of x g, then the derivative should be this, right? So like I said, I'm going to go a little slow. It's the derivative of the first one, right? X to the fifth. It's the derivative of that times sine x plus the derivative of sine x times the first function f, right? So this is f prime times g plus g prime times f. And I'm using the prime marks just to let you know on the next line I'm going to actually take the derivatives. So what is the derivative of x to the fifth power? 5x to the fourth, and that's just using the power rule, right? Power drops down, reduce the power by 1. And then sine x plus, now derivative of sine of x, which is cosine of x, times x to the fifth power. And that's what I refer to as the raw derivative. That's just, you applied the rule, that's the derivative. But we do want to be able to simplify this a little bit, all right? We want to try and clean these up if we can. So looking at these two terms, what factor do they both have in common? X to the fourth. So I could factor an x to the fourth out. And that would leave me with a 5 sine x. And then over here I took x to the fourth out, right? So it leaves me with 1x in here. Can I put that x together with that x? No, right? Because that's trapped in the cosine. That x out here is not. So what we do is we usually put it in front of the cosine so that you don't accidentally try and slap it together with that x on the outside. And that's all right. I mean, this is correct. This is correct. Just a different version of the correct answer. That is your derivative. All right, so that's how product rule works. Sure.
So a question real quick about this.
Yes.
If we were given a point and asked to find the slope of
The tangent line?
the tangent line at that point, we just input the x value and then get the slope of that, and then we could use use that to put it into the point slope formula to find the equation of that line?
Sure. I'll just add that on as a second part of this problem just so we can see how it was done. So there's a derivative. So let's say we started the problem. I gave you this function. I said, find equation of the tangent line at the point, let's see. Shoot, I'm going to have to go with something easy here. 0, 0. I had to find a point on the curve, so
Something that would work.
yeah. It's going to make this pretty boring, though, actually. It's going to be really boring. I think almost too boring.
If you went up, it wouldn't be defined the sign, right?
Well, I already know that my derivative is going to be 0.
Yeah.
Because when I plug 0 into this, I'm going to get 0. So the slope of my tangent line is 0. So it's just going to be a horizontal line. It's the x-axis, actually. But so can I make it a little more interesting? Yeah? All right, how about we just do at the point, see, that's why they make these so special. How about just 1 sine of 1? And that's what I would get if I plugged in 1, right? I'd get 1 here, and then sine of 1 is sine of 1, and I don't know what sine of 1 is. All right, so if you're going to find the equation tangent line, you need the slope of the tangent line, right? The slope of the tangent line, will be equal to the derivative at 1. It's the derivative at the value 1. Where am I getting this 1 from? The x-coordinate of the point, right? So plug 1 into this. So you get 1 to the 4th, that's 1. Sine of 1, 1 times cosine of 1. This is going to be 5 sine of 1 plus cosine of 1. And see, it's not a nice number that you're going to be able to figure out. You can get your calculator out, but okay. But this is a number, isn't it? So the equation of the tangent line, we'd use y minus y1 equals m times x minus x1. What's y1?
1. No,
Sine of 1. What's x1? 1. And what's the slope? This. So it's ugly. You asked for it. So I mean, I'm answering your question. You understand the method, though, right? The actual method. So y minus y1 sine of 1 equals m, which was 5 sine of 1 plus cosine of 1. And that's some number. That's an m. Then times x minus 1. I got kind of lucky there because x1 was 1. That's it.
Yeah, that's messy.
It is. Well, I'm not going to graph it. I don't want to check it. But you understand, right?
Yes.
Okay. All right, let's do another one. So that one was an easy one. Okay. You can do a harder one. Capital H of theta equals theta sine theta. Find H double prime of theta. So I want the second derivative. So you've got to take the derivative, and then after that, take the derivative again. So the variable in the problem is theta, right? Just like it was x before, now it's theta. So the derivative will be equal to, because I have a product, right? Here's my product. It'll be the derivative of theta times sine theta and then plus the derivative of sine theta times theta. What's the derivative of theta? 1. So this is like saying what's the derivative of x? And because theta is the variable, we treat it the same way. So this is 1 times sine theta. What's the derivative of sine of theta? Cosine of theta times theta. And I should take that theta back here and just slap it in front of the cosine so we don't accidentally think that that's theta squared. So we get 1 times sine theta is sine theta plus theta cosine theta. Anyone have a question on that part? We're good? That's just the first derivative. Now we must take the derivative of this. Now this is not initially a product rule, right? That's addition. So how do we take the derivative if we have addition between two things?
Would that be one thing together?
How do you mean?
Theta plus theta, that's going to be 1.
No, I'm saying sine theta plus theta cosine theta. That's two terms, isn't it? When you have two terms, like if you have f plus g, and you want to take the derivative, how do you do that?
Just add the derivative.
Just take the derivative individually, right? And add the answers together. It's not like product rule where there's some weird thing you have to do. This, we just take the derivative of this and then add to it the derivative of this. But this right here is a product, isn't it? So I'm going to have to apply the product rule just on this piece. The derivative of sine will be straightforward. Understand? So I'll write up here. H double prime of theta will be, now, do you want me to write it with all the primes still? You want me to do it that way? Keep doing it? Okay, so it's going to be what? The derivative of this? Yes? It's going to be the derivative of sine theta, whatever that is, plus, okay, now what's the derivative of this product? Derivative of theta, right? Derivative of the first one times the second one plus the derivative of the second one, which is cosine theta, derivative of that, times what? Times theta. So I'll show you again here. It's almost like we had another FG here, right? And this piece right here became F prime G plus G prime F. This guy right here is on its own. It's its own little problem. Understand that? Equals. What is the derivative of sine theta? Cosine theta. Plus derivative of theta, 1 times cosine theta. All right, derivative of cosine theta, negative sine theta. So look, I'm going to put plus here, but then I'm going to put in parentheses negative sine theta. And then times theta, right? And that theta doesn't change. Anything else I can do? How about that theta in front here? That theta right there in front, and then make this a minus. Also, can I put these together? Yes. This is 2 cosine theta, right, minus theta sine theta. Any questions? We good? Sure? Okay, so then let me add one more thing to this, because I said this one was going to be the hard one. Find H35 of x. What's that? What does that mean? The 35th derivative. So I'll come back next week. Y'all just stay here and work it out. and you'll have it. No, there's got to be something else. There's going to be a pattern here. There's got to be a pattern. All right, so let's write down what the derivatives were again. All right, let me erase this. The original function. Oh wait, sorry, of theta. Sorry, theta. The original function was theta. What? Sine theta? Okay. The first derivative turned out to be what? Was sine theta. Is that correct?
Plus theta cosine theta.
Plus theta cosine theta. Right? The second derivative, which we had written down, we've got it right here, is 2 cosine theta plus theta sine theta, isn't it? Oh, minus, thank you. Minus. Right? I want the 35th one. So you're supposed to do third derivative, then fourth, then fifth, then sixth, and seventh, eighth, ninth. All right, so let's see if we can pick a pattern up here. Let's do a couple of more derivatives, and hopefully we'll pick up a pattern and be able to like go out to the 35th one without actually having to do it. So what would the third derivative be? Well, what's the derivative of 2 cosine theta? So what do you do with the 2? Just bring it with us, right? It's coming along for the ride because it's attached to the function. So 2 is going to come with us. And derivative cosine theta is, what is it? Negative sine. So I should probably make that a negative 2 sine theta. You agree? Now I'm doing that one separate from this one because there's a subtraction, so I can do that, right? So then I say minus the derivative of theta sine theta, which is a product rule, right? But didn't we already do that?
Yeah.
Isn't this theta sine theta, isn't that exactly what I need to find the derivative of right now? What is the derivative of theta sine theta? It's this, isn't it? So I can say minus, without having to do the work, because I already did the work, it should be minus that expression, yes? So minus sine theta plus theta cosine theta. Is everybody following what I'm doing here? Any questions? All right, so now let me clean this up. When I put the minus sign through, right, this will become negative 2 sine theta minus sine theta, which is how many? Negative 3 sine theta. And then I have minus theta cosine theta. Don't we have that? Minus theta cosine theta. Question, yes?
I got lost. Why is it negative 3 sine theta?
If this distributes through here and here, this becomes a negative 1 sine theta. So you have negative 2 apples minus 1 apple is negative 3 apples. Yes? All right, well, I don't know if that made me any happier here. Fourth derivative now. See, what I was hoping is that this piece right here would be something we had taken the derivative of already. But we have, it's right there, right? So it's in our work from before. We'll get to that in a second. Fourth derivative. So I'm going to stop using the prime marks. I'm going to start using the parentheses with the number that tells you fourth derivative. What is the derivative of negative 3 sine theta? Negative 3 cosine theta. All right, minus, now look back in your work. We did the derivative of this a little while ago, didn't we? And didn't we get cosine theta, what was it, minus theta sine theta? Is that what we had? That's just product rule on this, isn't it? Clean this up. What do you get when you clean that up? Negative 4 cosine theta plus theta sine theta. Hey, that thing appeared again, didn't it? We got to keep going until we establish a pattern. I'm not convinced that we've established anything yet. Are you all convinced we have or no? A little bit? What do y'all see happening?
The coefficient at the beginning goes down.
This number right here?
It goes up
It
by
goes
one,
up by
but
one,
the
yeah.
sign changes every time.
Yeah, so what I think I'm going to do is I'm going to erase this so I can put these all together so I can see them next to each other. That was my third derivative, right? My fourth derivative, which I just got, is that answer down there. And I'm about to work on my fifth derivative, right? Okay, so tell me about the pattern again that you're seeing.
The coefficient is going up by one, so
Okay, so like that coefficient is 1. The first derivative, that was 1, and then there was 2, and then it was 3, and then this is 4. So it looks like it might be a 5 next.
The sign's gonna change every two primes. Okay.
And then it was positive, positive, negative, negative. Maybe it's going to be positive, positive again.
Yeah.
Okay. What about all the other stuff, though? Sine, cosine, sine, cosine.
it alternates.
Theta, cosine, theta, theta, sine, theta, theta, cosine, theta, theta, sine, theta.
That's gonna be,
So maybe it's going to keep alternating? Let's just see. I think maybe we need another 1 or 2 derivatives to be convinced of something, yes? All right, so let's try it. By the way, this problem is right out of the book, so I'm not just making up like hard problems. This is number 36 in the book. But they use x instead of theta. All right, so fifth derivative. Help me out here. Fifth derivative. So I take the derivative right here, right?
So would it go back to positive now?
It's going to go back to positive because,
Five sine theta?
yeah, you ignored the negative 4, right? Derivative cosine theta is negative sine theta. But then you bring the negative 4 back in. Now it's positive 4. Understand? When is the I thought the derivative constant was 0. When it's by itself. See, it's not by itself. It's attached to a function, so it just comes for the ride. So what are you saying here? Positive 4?
5 sine theta.
Not yet. Not yet. Right? Well, you're already going for the pattern. Okay, I'm actually taking the derivative again. Yeah. Because I want to convince myself of this pattern. And then I need the derivative of this, don't I? Which was this right here, which the derivative is right there. So I'm going to have, what do we have? Plus sine theta plus theta cosine theta.
The first term should be 4 sine.
Oh, 4 sine. Thank you. Thank you. Yes. Thank you. Derivative of cosine is negative sine. My apologies. This one should have been 4 sine. I'm glad it was because I was like, damn, our pattern just blew up in our face. So the fifth derivative looks like it is 4, 5, right? Because I'm putting these two together. 5 sine thetas plus theta cosine theta. So is everyone so far convinced that the numbers keep going up? Yes?
sign changes.
The sign's changing. I'm not quite sold on that double. It looks like it's going to be double positive, double negative, double positive. I might be convinced if we do it one more time. These are pretty, well, are these?
There's a pattern.
Is there a pattern though? What about the signs though?
Yeah.
Plus, negative,
That is plus.
negative, plus, plus, negative, negative on the next ones?
Well,
Yeah.
technically you're doing, on the original equation, it's positive 2.
Right.
Where?
Plus, plus, minus, minus, plus, plus.
Oh yeah, if you go back and look at that as your 0th derivative, yeah. Yeah, by the way, the 0th derivative is the function without taking the derivative, by the way. Right, first derivative, second derivative, third, fourth, fifth, 0th derivative. That comes in Cal 2. Yeah, Cal 2. Wait, later in Cal 2, sorry. Forgot where I was. This is Cal, no, this is Cal 1, okay. I'm sorry, it's Monday. Forget what class I'm in, I'm like, wait a minute. Oh, that comes in at the end of Cal 2 in what are called Taylor series. You have the 0th derivative, which means don't take the derivative. All right. 6. I'm going to try and convince myself. I think I need 2 more. What do you need? 1 more or are y'all done?
1 more.
1 more? Okay. Derivative of 4 sine theta is 4 cosine theta. 5. Damn it. I didn't write down. Doing this one. Man, it's Monday. It's a super Monday for me right now. Okay. Taking derivative of this. Help me out. 5 cosine theta plus, we've done this twice now, right? So it's cosine theta. I don't necessarily need the parentheses, but I'm going to put it, or brackets. Cosine theta minus theta sine theta. Put it together, you get the 6th derivative, which is how many cosines? 6. That's refreshing. And it's positive. That's refreshing. Cosine theta. And then minus theta sine theta. Was that what we were hoping for? Yeah, I think so. I think we've got it. So it looks like we can get the pattern, but where's 35th derivative in this pattern?
Can we do that like a 3 on the
35 sine theta.
The 3 on the what?
I mean like just changing the 35 sine theta
This one right here?
since it's the 5th.
Since it's the 5th? Okay, I think you're onto it. So look at this. I think we have enough to see that it's like a cycle that's repeating itself. At least it appears that way. The first one and the 5th one appear to do the same sort of thing, don't they? They're both positive, right? 5th power is 5 in front here, right? Cosine, or theta cosine, theta cosine.
And they are numbers, both variables are the same sign.
Everything matches. The only difference is the 5, right? That's the only difference. Let's see, does the 2nd and the 6th one do the same thing? Do those 2 do the same?
Yeah.
They both have cosine, cosine, minus, minus, theta, sine, theta. They're exactly the same, except for a 2 and a 6, right? And then it makes sense that maybe the 3rd and the what? 7th one, which I haven't done, should probably do the same thing. And then maybe the 4th one and the 8th one. Right? And then the 5th one and the 10th one. So the first one will do the same as the 5th, which will do the same as the 10th, which will do the same as the 15, 20, 25, 30, 35. So here is our projection, right, as to what we think it is. The 35th derivative should be 35 sine theta plus theta cosine theta. What do y'all think? Yes? So that was a harder problem, just because you have to really think through it, right? It's not just as mechanical as do this, that, put together, done. Anybody have a question on that? Okay, quotient rule time. Same section. The quotient rule and the product rule are in the same section, which is 2.4. Now, I'm not going to prove the quotient rule just because of time. It would be nice to do the limit proof, but so quotient, product was when you multiply 2 things, quotient's when you divide 2 things. So if you have a quotient, some function on top of some other function through division, and you want to find the derivative, also, g can't be 0, or else you can't even do it, right? G can't be 0. But as long as your function on the bottom is non-zero, then the quotient should be, wow. Well, this is, don't write it down. This is what we wish it was, right? That's what we wish it was. That you did derivative of each one and divided. That's what we wish it was, but it's not. Just like the product didn't work this way, quotient doesn't either. So let's see if this looks familiar to you. That look familiar so far?
Yeah.
Change the sign? That's the product rule with the sign changed, right? Yes? One more thing. Divide the entire thing by g squared, which is the bottom function with no derivative, just squaring it. Now that's really a weird formula, all right? There's a lot going on in here. But it's very connected to the product rule, right? So I don't know if you remember last week I told you that the books do the formula different ways, but they're all the same with the product rule. Do you remember me saying that? Like the book might have like GF prime plus FG prime or something like that. What does this book have? I'm going to tell you what this book has for product rule.
It's more complicated.
It looks more complicated, but it's the same thing. So your book says that if you have a product, that you should do F times the derivative of G plus G times the derivative of F. That's what your book says the product rule is. Now up here in the corner, I'm going to remind you what I said it is. What did I say the product rule was? That's what I said, right? And they're the same thing, right? Addition, it doesn't matter. I can flip those over, and then just flip them over, and that's the same thing, right? But let me show you what the book says the quotient rule is. The book says that if you take F over G, it's G F prime minus F G prime over G squared. Is this the same as what I have up here? Yeah, they just switch this and switch this, right? So why do I do it this way as opposed to doing the book? Alphabetical order, yes, but there's something else here. Look, don't these seem like completely different formulas? Like look at the product rule. FG prime plus GF prime. This one, GF prime minus FG prime, totally different kind of things, right? And then divide by G squared. Whereas if you do it this way, the only difference between these two formulas is what? A minus and a G squared, and that's it. So if you can memorize the product rule and know that the quotient's just minus divide by G squared, then you only really have to remember one thing, right? This just to me, when I was a student, seemed like totally different things. It's like, and my brain doesn't like memorizing totally different things. My brain doesn't like memorizing anything. But, okay, so that's why I do it that way. I'm just trying to point that out to you. So if you do get help, get someone that tutors you or something, a lot of them, they learned it this way, and so that's the way they have it memorized, and that's the way they want to do it. But just tell them this is the way we're doing it in class, so please help me using that way. It's the same formula. All right, so you want to see the quotient rule in action? Of course you do. Before I do it, though, a couple of other things with the language here. We say if you have f times g, the derivative is f prime g plus g prime f, right? But I don't know if you've picked up on this. What I've been talking through derivative, I've been saying things like the derivative of the first one times the second one plus the derivative of the second one times the first one. Do you understand what I meant by that? Derivative of the first one times the second one plus derivative of the second one times the first one. All right, that's another way to remember the product rule. So that way you're not thinking fg, just whatever the function is, the first one, derivative of that times the second one, plus derivative of the second one times the first one. Now that's going to come into play when we look at this right here. With the quotient, okay, we could say it's the derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared, right? Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. And there's even some cute little things that I've seen in other classes I'm not going to talk about. It's like a cute little saying that helps you remember it. But these two things need to be hardwired, okay? These are not like, where's my formula sheet? You've got to memorize these formulas. From here on out, you're going to be using them all the time. So I want to get used to them. All right, so let's see it in action now. The quotient rule. So I've got to give you a quotient, right, in order to use the quotient rule? So as an example, let's let, I'll use h again. H of x is equal to x cubed plus 4x squared plus x minus 1 over 3x to the 6th plus x to the 4th minus 1. So that's a good old like rational function, isn't it? Rational function from college algebra, nasty looking one. What is its derivative? That means we should be able to find the slope of the tangent line at any point on that graph if we can find this derivative. So is it kind of glaring that this is a quotient? Yes? And so what we can do is identify the top function, which we'll call f. It's everything we see up here, right? Everything. The bottom function here, which is g. And then we just apply the formula, f prime g minus g prime f all over g squared. So when we apply the formula, the derivative of h should be the derivative of the top, right, times the bottom, minus the derivative of the bottom. There's my derivative, times the top, all over the bottom squared. That's the derivative. Now, I haven't even taken a derivative, have I? All I've done is just applied the formula, just like showing you where I'm going to be taking derivatives here, and then everything else I'm not even touching. All right, so our next line, we should probably just go ahead and take those derivatives. What is the derivative of this here? 3x squared. You know, I think I'm going to do it up here. 3x squared, what? 8x plus 1. Done? Times the next function. Minus derivative of this one. 18x to the 5th.
Plus 3x to the 3rd.
4x to the 3rd.
4x to the 3rd, sorry.
No, that's all right. And then derivative of this is 0. Then times the next one. Oh. All over the bottom squared. Done. That's the derivative. Now, what we could do is we could actually multiply this out. Now, that would not be fun, but we could multiply that out. We could multiply this out. We could collect all of our like terms together and just kind of clean this thing up, right? But that would just be algebra. Not fun algebra, but algebra.
Can you cancel like?
Well, you can only cancel it if it's common to all of them. And like, you could not cancel this with this because you would need this to appear over here also. Right, but do you understand at least the format of this? Derivative of top times bottom minus derivative of bottom times top all over bottom squared. Now you may be looking at it going, well, that sucks. You know, that's a pain in the butt, right? But always keep in mind how much better that is then this would have been f of x plus h, right? Would have been that entire rational function with all your x's replaced with x plus h's. And then minus f of x with all those, and then all over h, and then have fun with it. There's just no way. So even though this is tedious, it's not this type of tedious, which would be insurmountable. All right.
Would that be the derivative?
Hmm?
Just that equation would be the derivative.
That would be the derivative, yep. Now let's do one where we clean it up a little bit. That was too much to have to clean up. How about f of x equals x minus 2 over x squared plus 4? All right, so do you see the quotient?
No question.
Yes.
If that was the difference, would you go ahead
You
and
would
factor it out
cancel,
first?
yeah, you would cancel it out. Yep.
So it'd be 1.
If the bottom was x squared minus 4, you would factor out and cancel, and then do your derivative after that.
Okay.
We'll never use eyes in calculus, huh?
Not in this book.
Using that.
Yeah, I want you all, will you all do this one real quick while I take this real quick? All right, sorry about that. I'm going to work it out while y'all are there, and you can do it, and you can check your work with me. That's it.
Well, I erased it, but what if we simplified x? No, but it's prime.
It's not a, yeah, it's not a difference of square.
Okay.
How to get what? Plus 4. Right here? So this is like a negative 2x distributing through to x minus 2. So here to here is negative 2x squared. And then here to here is positive 4. Is that what you're asking about?
4x.
Oh, 4x. Oh, that's what you're asking about. Yeah, that's, okay, so I went too fast.
Take an X out?
No, this is going to change things. Hold on. This is going to be, does it factor after this?
No, it doesn't.
I went too quick. Hold on. That's the x, and then, so when you do this, what, negative x squared plus 4x plus 4. Okay. Thank you.
Now, can you FOIL off the denominator?
You could, but you don't necessarily need to. Yes?
If the x squared plus 4 were not prime, can you factor it?
Yeah, that's what we were saying. If that was a difference of squares, you would factor and cancel. Yeah. Okay, y'all understand? Anyone have a question on this? Other than being careful when you distribute?
So you can't pull out an X from there, right? Make it a minus 2X plus 4
Where?
from right there, yeah, where you're at.
Here?
You can't pull out an X? No. So it would be, oh, yeah, okay, you just start with this.
Not from everything. I don't know if that's what you meant, but.
Okay, I see.
All right, so that's that derivative, right? Let me ask you, what about this? I changed the problem a little bit. You still have quotient rule? Yes? So you have a top and a bottom function, right? So according to the quotient rule, the derivative will be the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared, yeah? What is the derivative? Are we okay on this?
No, it's gonna be 0, so the whole
The
left
derivative of 1 is 0,
side, so it's just
and that's going to kill off the entire left side. But you still have this, right?
Negative 2x.
This is going to be, derivative of this is 2x and then negative and then times 1. So just negative 2x on top is all that's left? All over x squared plus 4 squared. That's it. I just wanted you to see what happens if you have a constant on top like that. When you do have a constant on top, this left side will always go to 0. But you still have something here that you have to mess with. Questions? Okay, let's try something else. Okay, good. Who said that? Derivative of tangent x is secant squared x, right? Let's see why. All right, let's see why it's secant squared x. What is the definition of tangent of x from pre-cal? Sine over cosine, isn't it? That's the definition of tangent. Now, I proved to you in class using the limit that the derivative of sine of x is cosine x. And I asked you as a bonus take-home to try and figure out prove using the limit that the derivative of cosine of x is negative sine x. So you could prove both of those with the limits, couldn't you? But now that that's proven, we can actually find the derivative of tangent of x using the quotient rule. Right? So go ahead.
Can you just put it over 1 and do it like that?
Well, this is a quotient. I don't know if that's what you meant, but
No, tangent over x over 1, and just make that.
yes, but let's act like we don't know the derivative of secant squared. That's what I want us to do here. Where did that formula come from? Right? Where did it come from? Well, here's where it came from. First of all, we proved these two precisely using the definition. So we know their derivatives using the limit. Now that we know that, if I want to know the derivative of this, I have a quotient, sine and cosine. It should be the derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared, yes? So derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. Is it all right if I write the bottom squared that way? What is the derivative of the top? I'm sorry, this one right here. Cosine x times cosine x again minus, what's the derivative of cosine x? Negative sine x times sine x again, right? All over cosine squared x. You'll see what happens up there? What does that negative and negative do? Becomes a plus. So this is the same as cosine, I heard someone say it, cosine squared x. What? Plus sine squared x over cosine squared x. What is this?
That's 1.
That's 1. That's the Pythagorean identity from pre-cal. So the top is equal to 1, right? 1 over cosine squared x. But that's the same as 1 over cosine x squared, isn't it? And 1 over cosine is secant, which is secant squared x. So derivative of tangent x is secant squared x, and you can show it using the quotient rule. So I couldn't show you that until we had the quotient rule. Make sense? You can use this same method to show that the derivative of secant x is negative, that the derivative of secant of x is secant x tangent x. You can do this to show that the derivative of cosecant x is negative cosecant x cotangent x. And you can use this to show the derivative of cotangent x is negative cosecant squared x. Yes? Right?
Is that our next extra bit?
No, but that would be fun. I mean, just for fun, you know? I know you like to do things for fun. All right, so let's just kind of retrace. We got 30 minutes left, but let's just kind of retrace things. We started this class with the idea of the limit, right? And with the limit, we could start talking about approaching things and infinity and all these different concepts. And then from that, we built up this idea of this thing called the limit, which represents the slope of a tangent line on a function. I'm sorry, the derivative, which was the slope of a tangent line on a function. And we realized that those limits can get pretty ugly. And we started coming up with rules. And the first rule we established was, the first big rule was the power rule, right? That you bring the power down. And then from that, we developed the product rule. And now we have the quotient rule. And what we're starting to realize is that these rules, although they are powerful, they are they're opening up the Pandora's box of the types of functions we can differentiate. Now we can get more and more complicated functions. And so this next example is to show you how, be careful what you wish for. Where you're like, well, where are those rules that everyone's been telling me about? Like, okay, well, you got them now, so let's see what you do with something like this. So what if you have like x squared sine x over 1 plus tangent x? That's a function, right?
You use both rules?
How do you mean?
Top one's a product. Yeah.
You have a product up top, and the whole thing is part of a quotient, right? So you got a mixture in this problem of two different things happening. But overall, would you agree that the quotient is like the big thing happening?
Yeah.
So like I could treat this whole thing as like f and g, although I'm already using f. So top and bottom, right? And I can just set up the formula using the quotient rule. This should be, now see, once you get to a point where you're really like kind of comfortable with quotient rule, you start to realize that this is just like a fill in the blank thing, right? Right? That's all quotient rule is ever going to be. That fill in the blank thing. What's the top left? What gets pasted in here?
2 cosine x?
Hold on, we haven't taken derivative, right? The prime mark means I'm going to take derivative in a minute. X squared sine x goes here, right? And then here, 1 plus tangent x. And then here, 1 plus tangent x. And then here, x squared sine x. And then down here. That's just simply plugging everything into the formula, right? I haven't done any derivatives. Now I have to take a derivative, don't I? I have to take two of them. Take this one and this one. But this is where you recognize, hopefully you recognize, that this derivative right here is not as simple as just, 2x times cosine x, because it's what? It's a product. So when you go to take the derivative of that piece, you actually have to apply the product rule to it, don't you? So that's separate work that I'm going to do over here on the side. Scratch work, SW scratch work. This is my side work. Okay, I'm going to find the derivative over here of x squared sine x. And whatever I get as this answer, I'm going to plug in back here. So let's see if we can talk through this one. What is the derivative of this? 2x times sine x plus cosine x times x squared. So it's the derivative of the first one times the second one plus the derivative of the second one times the first one. And maybe I'll clean it up. 2x sine x plus x squared cosine x.
Minus cosine x?
The derivative of sine is cosine, not the other way.
Oh,
Derivative of cosine is negative sine. Right, so do we all agree the top left corner of that quotient rule is this? So that's going to go here. All right, then I'll multiply times that. And then this right here, what's the derivative of this? Am I going to need a special rule, or are we okay?
You can do it separately, so it just be 0.
Derivative of 1 is 0. Derivative of tangent,
Yeah,
secant squared x. So that shouldn't, I don't think I need scratch work for that, right?